In this video, I will review some examples related to ration function, exponential function, and logarithmic function. Example 1. Find all vertical and horizontal asymptotes of the graph of the ration function and enter your answer as a comma-separated list of equations. So here the function is h of x equals to 528x minus 1000 over 100 minus x. Vertical asymptotes. To find the vertical asymptotes of function h of x equals to 528x minus 1000 over 100 minus x, first you simplify. As you notice, we cannot simplify further. So it's already simplified. So to find the vertical asymptote, all you have to do is to set the denominator to 0. So the denominator is 100 minus x. So we have 100 minus x equal to 0. So now we're going to solve for x. So since x is negative, so you can move the minus x to the right side. So it becomes positive 100. So we have 100 equals to x. This we can write x equal to 100, and that is the vertical asymptote. Make sure write x equal to 100, not just put 100, because vertical asymptote is a vertical line, and vertical line has an equation of x equals to 100. So next we're going to find horizontal asymptote of this function h of x equals to 528x minus 1000 over 100 minus x. To find the horizontal asymptote, we're going to check the degree of the numerator. So n is the degree of numerator, and that's the highest exponent of x, and this x has the highest exponent, and that's 1. And m is the degree of denominator, and that's also the highest degree of x on the denominator. So here x has an exponent of 1. So the degree of numerator is 1, the degree of denominator is 1, and the degree of numerator equals to degree of denominator. So the theory says the horizontal asymptote is y equals to leading coefficient on the numerator. And what is and divide by the leading coefficient on the denominator. So leading coefficient on the numerator is the number multiplied with the highest degree term. So we have a 528x. So 528 is the leading coefficient on the numerator. And this x, then the number part of minus x is negative 1. So that's the leading coefficient on the denominator. So we have y equals to 528 over minus 1. If you simplify, you get y equals to minus 528. So that is the horizontal asymptote. Here's an example 2. We are given a function f of x equal to x squared minus 1 over x plus 3. So first we're going to find intercepts. Now remember, there are two kinds of intercepts, x-intercepts and y-intercepts. So let's find x-intercepts first. So we set this function to 0, which means x squared minus 1 over x plus 1 equals 0. Now we multiply both sides by LCD, which is x plus 1. So we get x plus 1 times x squared minus 1 over x plus 1 equal to 0 times x plus 1. So I didn't put, because x plus 1 times 0 is 0. So now we simplify. Looks like x plus 1 cancel with x plus 1, and you're left with x squared minus 1 equal to 0. So now we're going to solve for x. So I think we can factor x squared minus 1, which are x plus 1 and x minus 1. And since the product x plus 1 and x minus 1 equal to 0, we can set each factor to 0. So the first factor is x plus 1, we set that to 0, and then we set x minus 1 to 0. So let's see, solve x plus 1 equal to 0, we move the 1 to the right, and you get x equal to minus 1. Similarly, here we move the minus 1 to the right, it becomes plus 1, and we have x equals to 1. So the x-intercepts are, the lowest x value is negative 1, comma 0, and then 1, comma 0. So we have two x-intercepts for this rational function. Next, we find the y-intercept. While you find the y-intercept, you have to do is substitute x equal to 0 in the equation. So we're going to substitute x equal to 0 in this equation, y equals to x squared minus 1 over x plus 1. So this becomes y equal to 0 squared minus 1 over 0 plus 1. So 0 squared minus 1 is just a minus 1, and 0 plus 1 is just 1. So you have a negative 1 over 1, so which becomes a negative 1. So y equal to negative 1. So now the y-intercept is y equals to minus 1. Part B. Find any asymptotes. Let's first try vertical asymptote. So let's look at the function and first simplify. And to simplify, we're going to factor x squared minus 1, which are x minus 1, x plus 1, divide by x plus 1. You can see it cancel out, and you get x minus 1. Now it's a polynomial, and polynomial function has no vertical asymptote. So this rational function does not have a vertical asymptote. Okay, now we try to find horizontal asymptote. To find the horizontal asymptote, we have to find the degree of the numerator. In this case, n is 2. And m is the degree of the denominator, and that's what, 1. Now the degree n is bigger than m, and the theory says no horizontal asymptote. So let's try find slant asymptote. So let's check the degree of the numerator, which is 2, and the degree of denominator, which is 1. So here n is bigger than m by what? How much? N is bigger than m by 1. So theory says that there is a slant asymptote. Now the next thing, how do you find the slant asymptote? Well, to find the slant asymptote, you divide the numerator by the denominator. So you write I'm going to use syntactic division. The coefficient of x squared is 1, so I'm going to put. Now after x squared, there should be an x, but there's no x term, so I will use 0. After that is a constant, minus 1, so I'm going to use the constant. Now I have to divide by x plus 1. So in order to do the syntactic division, I need a number to divide. So I will take x plus 1 equal to 0 and x equal to what? Negative 1. So I'm going to divide by negative 1. So now how syntactic division works? We have bring down the first number as it is, and then you multiply negative 1 times 1 and put under the next column. So it becomes negative 1 here. Now we add. So you add 0 into negative 1, it will be negative 1. Now we multiply negative 1 with a negative 1, it gives you plus 1. And now we have a negative 1 here and plus 1 we can add and become what? 0. So the remainder here is 0. But we need slant asymptote. The slant asymptote is y equals to the quotient. What is the quotient? Quotient is 1 times x minus 1. So we can set this to equals to y. So the slant asymptote is y equals to x minus 1. Okay, so now we have found the x-intercepts negative 1 comma 0 and 1 comma 0, and y-intercept we found 0 comma negative 1, and we found slant asymptote y equals to x minus 1. So now we plot these points, negative 1 0 1 0 0 negative 1. So negative 1 0 is here, and 1 0 is this one, and this is 0 negative 1. So we connect this line to a line passing this one. Now this graph will never pass through this one, so we put this point where the minus 1 is, put an open circle. Okay. So that's the graph of this the rational function in this case. Example 3, application of one-to-one property of exponential functions. You use the one-to-one property to solve the equation for x. So equation is 3 to the power 2x minus 1 over 1 over 81. So let's start with this again. 3 to the power 2x minus 1 equals to 1 over 81. If you look at these numbers, 3 and 81, they are, in some way, they are related. So 81 we can rewrite as 3 to the power 4. So 1 over 81 we can write as 1 over 3 to the 4. Now we can move the 3 to the 4 to the top and become 3 to the minus 4. So this equation becomes 3 to the 2x minus 1 equal to 3 to the minus 4. As you can see, both sides have same basis. So one property says that we can drop the basis and equate the exponents. So we get 2x minus 1 equals to negative 4. Now it's a simple linear equation, so you can move negative 1 to the right side. So you will have 2x equals to minus 4 plus 1. Now minus 4 plus 1 we can add, it becomes negative 3. So now we have a 2x equal to minus 3. So we can divide by 2. So you get x equal to negative 3 over 2. So solution set is negative 3 over 2. So example 4. We're going to use one-to-one property to solve the equation for x. So the equation is e to the x squared minus 54 equals to e to the 3x. So we see, if you look at this equation, both sides have same basis e. So one-to-one property says we can equate the exponents. So we'll get x squared minus 54 equals to 3x. Now it looks like a quadratic equation. So in this case, we move all the terms to the left side. So we move 3x to the left side, we get x squared minus 3x minus 54. And now we have a 0 equal to 0. We can factor this trinomial. Well, factors of x squared are x times x, and the factors of minus 54, minus 9 and 6. As you can see, if I multiply negative 9 with 6, it becomes negative 54. But if I add negative 9 to plus 6, it becomes negative 3. So these are correct factors. Now we set each factor to 0. So x minus 9 equals 0. And if I move the 9 minus 9 to the right side, I get x equal to 9. Now I set the second factor x plus 6 equals 0 and move the 6 to the right, we get x equal to negative 6. So solution set is negative 6 and positive 9. Example 5, continuous compounding. You invest $50,000 in a fund that pays 4.5% interest, compounded continuously. How much will you receive after 30 years? So in this example, we are given $50,000, which we say P, because P stands for principal, and principal means the money invested. Since we are investing $50,000, so P would be 50,000. Now, this is the interest rate, so R is 4.5%. It's compounded continuously. That's very important. Now, continuously means I have to use a formula which is for continuous compounding, and that is A equals to P times e to the power RT. Now 4.5% you can also change into decimals, it becomes 0.045. Now T is given 30 years. So I'm using this formula because it's a continuous compounding. So all I have to do is substitute P equal to 50,000, R equal to 0.05, and T is 30. So I get A equals to 50,000 times e to the 0.05 times 30, and now put on this calculator and you should try to get 192,871.28. Example 6, not continuous compounding. You invest $50,000 in a fund that pays 4.5% interest, compounded quarterly. How much will you receive after 30 years? So let's see what is given. We are given $50,000 to invest, so we can call this P. So P is 50,000. and R is the interest rate 4.5%, and it says compounded quarterly. So change 4.5% to a decimal, move the decimal 2 places to the left side, so it becomes 0.045. Now T is 30 years. Now the compounding is quarterly, so we have to use this formula. A equals to P times 1 plus R over N to the power N times T. Now we substitute P equal to 50,000, R equal to 0.045, and T is 30. But what is N? Well, it's a compounded quarterly. So how many quarters in a year? 4 quarters. So we're going to substitute N equals to 4 here. So this becomes A equals to $50,000, parentheses 1 plus 0.045 over 4 to the power 4 times 30. Now you can use the scientific calculator and try to get $191,423.02. Example 7. Domain of logarithmic function. So we're going to find the domain of logarithmic function f of x equal to log of x minus 3. Now this log has a base of 10, and this log is called common logarithm. Now to find the domain of the logarithmic function, all you have to do is just set the argument. X minus 3 is the argument, set to greater than 0. So you have inequality x minus 3 greater than 0, and it's a simple linear inequality. So you move the negative 3 to the right side. So you get x bigger than 3. Now write this as an interval, bigger than 3, 4, 5. So we write 3 comma infinity and parentheses. So that's the domain of this logarithmic function. Next, we're going to find x-intercepts of the logarithmic functions. So same function f of x equal log of x minus 3. So to find the x-intercepts, we know we set function to 0. So we're going to set log of x minus 3 equal to 0. Now one side has a log, the other has a number. So we can change to exponential form. So since the log has no base, it means this log stands for common logarithm, and its base is 10. So we're going to write 10 to the power 0 equals to argument of the log s minus 3. Now 10 to 0 is 1. So we have x minus 3 equals to 1. So simple linear equation, move the negative 3 to the right, we get x equal to 1 plus 3, which is 4. So you get x-intercept 4 comma 0. Next we're going to find the vertical asymptote of the logarithmic function. So to find the vertical asymptote, we set the argument of the logarithmic function to 0. So we'll set x minus 3 equal to 0, and we set the argument to 0, so it becomes we get x minus 3 equal to 0. And simple linear equation solve for x, move the minus 3 to the right, we get x equal to 3. So x equal to 3 is the vertical asymptote. And now we already have found x-intercept 4 comma 0 and the vertical asymptote, and we know the domain is 3 and to infinity. So we draw the vertical, this is vertical asymptote, and this is the x-intercept. So this graph, you can choose a few more points and it's going to get this graph. And that's the graph of the logarithmic function f of x equal to log of x minus 3. So here is example 10. We condense the expression to the logarithm of a single quantity. So we have a log of x minus bracket log of x plus 1 plus log of x minus 1 bracket close. So first we condense the terms we have within the bracket. So we apply, since it's a plus here, so we can use the product rule, so which is log of u base a plus log of v base A is log of u v base A. So we write the log once and just multiply x plus 1 and x minus 1. Think of x plus 1 like a u and x minus 1 is what? Like a v. So now we have a log of x minus log of x plus 1 times x minus 1. Now there's a minus in the middle of two log, so we apply this. It's called quotient rule. Log of u base A minus log of v base A, which becomes log of u over v base A. So now I think u is your x and v is your this whole thing. So now I can write the log once and you divide x over this. So now we have a log of a single quantity. Example 11. So we're going to condense this expression 1 over 4 bracket log of x plus 1 plus 2 log of x minus 1 bracket close minus 6 times log of x. In order to apply those product and quotient rule, where we make sure no number is multiplying to any log. Now you can see the 2 is multiplying to log of x minus 1 and 6 is multiplying to log of x. So first we apply the power rule of logarithms. So let's go. Let's say we write 1 over 4 bracket log of x plus 1 plus 2 times log of x minus 1 bracket close minus 6 times log of x. So we're going to apply the power rule and we can on 2 log of x minus 1 and 6 log of x. So the power rule says that you move the power and make an exponent of the arguments. So this becomes log of x minus 1 square and this becomes log of x to the 6. And everything you just copy it 1 over 4 bracket log of x plus 1 plus log of x minus 1 square minus log of x to the power 6. So now first we convert this into single quantity, plus mean we multiply. So we write 1 over 4 log of x plus 1 times x minus 1 square. And just copy this one minus log of x to the 6. Now this is single log and this is being multiplied with 1 over 4. So first we apply the power rule on this one and move the 1/4 as an exponent of this whole expression. So it is going to look like this log of parenthesis x plus 1 times x minus 1 square parenthesis and then to the power 1/4 and just bring down minus log of x to the 6. And now that we have a difference of logs, in other words a log of something minus log of 6. So we apply the quotient rule. So quotient rule says you write the log and then take this one, write it as a numerator and then x to 6 as denominator. So now we have a log of a single quantity. Now since this expression is a power of 4, so we can change to radical form. So this becomes log of 4th root of x plus 1 times x minus 1 square over x to the power 6. Example 12. So it says expand the given expression as sum, difference or constant multiple of logarithms. So we have a log of base 2 x square y cube over z square w. So it looks like this is a quotient. So we apply the quotient rule first. And the quotient rule is log of u over v base 2 is a log of u base 2 minus log of v base 2. So we can write the log of 2 and then write the numerator. And accordingly put minus here and then write log of 2 again and write the denominator. So now we have, if you look at each logarithm, after log looks like they're multiplying x square and y cube and z square and w. So on each log we're going to apply the product rule. So product rule says the log of u v base 2 is a log of u base 2 plus log of v base 2. So I can write this log of x square y cube as log of x square base 2, and according to this one I put a plus and write log of y cube base 2. Now it's a minus, so I'm going to start with the parenthesis and then again apply the product rule. So I'm going to write log of base 2 of c squared, and then this means plus log of w base 2. Now I'm going to distribute the minus, and so it becomes log of x cube base 2 plus log of y cube base 2, and minus, if I distribute, becomes log of z square base 2, and minus and plus makes it minus log of w base 2. Now we apply, since a log, after log this is exponential x squared, I apply the power rule, so I rewrite as 2 log of x base 2. And then put plus and then log of y cube, apply the rule again and bring the 3 down and multiply log of y base 2. And then it's again z squared, it's exponential, apply the power rule and bring the power mean down and put in the front of the log and write log of z base 2. This is okay, so we just copy it, minus log of w base 2. So that's the, we have a sum difference of n constant multiple of logs. And that's what we want. So we have expanded log of a single quantity into 1, 2, 3, 4 logs. So here is an example 13, solving exponential equations. So we're going to solve this exponential equation. 2 times e to the x minus 4 equals to 11. So whenever you see an equation and one of the term has exponential, so first try to isolate that. So we're going to isolate e to the x. So we can maybe move negative 4 to the right and then divide by 2. So you will get e to the x equal to 11 plus 4 divided by 2, which is 50 number 2, which is equal to 7.5. Now we have e to the x equal to 7.5. Now there's no way I can write 7.5 e to the some power. So in this kind of situation, you always take the natural log. So you put the natural log in the front of each side. So it becomes natural log of e to the x, and it becomes natural log of 7.5. Now we try to simplify. Now if you notice, natural log has a base of e, and the exponential has a base of e. So the base cancels according to inverse property of log, which is log of a to the x base a, which is x. So according to this, they cancel out and give you the exponent x. So it's become equal to natural log of 7.5. We are done. Just use the calculator and down to 3 decimal places. So the answer is x equal to 2.015. Example 14. So we're going to solve this equation, e to the 2x minus 7 times e to the x plus 12 equal to 0. So e to the 2x minus 7 times e to the x plus 12 equal to 0. So this looks like an equation in standard form, so we're going to try to write in standard form. So we can write e to the 2x, e to the x to the power 2 minus 7 times e to the x. So it looks like the first term is the square of the second term. I mean this in the variable, in terms of variable term. So we can factor, so e to the x square we can factor as e to the x, and 12 we can factor out minus 3 times negative 4. And you can see negative 3 times negative 4 is what? Positive 12. But when you add negative 3 into negative 4, it becomes negative 7. So these are correct factors. So since we have a product of two factors and it's equal to 0, so we can rewrite each as each factor equal to 0. So we get e to the x minus equal to 0 and e to the x minus 4 equal to 0. So isolate, move the minus 3 to the right, we have a e to the x equal to 3. And now to solve, and similarly e to the x equal to 4. Now we rewrite in exponential form, so we can write x and we can log of 3. Since e has a base of 3, so become natural log of 3. Similarly, this we write x and log of 4. So now we put on the calculator down to 3 decimal places, so we get x equal to 1.099, and here we get x equal to 1.386, and these are. Example 15. We're going to solve the logarithmic equation algebraically, and then we approximate result to 3 decimal places. So let's start with this. Log of x plus 1 minus log of x minus 2 equal to log of x. So what you see is left side we have a 2 logarithm, right side has a 1 logarithm. So we can combine this into single logarithm. Since the minus in the middle, so probably we can apply the quotient rule. So this becomes log of x plus 1 over x minus 2 and equals to log of x. So what do you see here? You have a log on both sides, and one-to-one property says you can drop the logs and equate their argument. So we can say drop the logs and we write x plus 1 over x minus 2 equals to x. And now we have a rational equation. So we can cross multiply. So you can multiply x with x minus 2 and x plus 1 with 1. So we have a x times x minus 2 equal to x plus 1. Distribute x, it becomes x squared minus 2x equal to x plus 1. And since one of the term is a square term, so it looks like it's a quadratic equation. So we move all the terms to the left side and make 0 right side. So now you have x squared minus 2x minus x minus 1. So it looks like we can combine this one and we can rewrite as x squared minus 3x minus 1. Looking at this one, it looks like it's not factorable. So what are we going to do? We're going to use a quadratic formula. So A is the number part of x squared term, so A is 1, B is negative 3, and C is equal to negative 1. And the quadratic formula is x equals to negative b plus minus square root of b squared minus 4ac. So we substitute with the b is negative, so we got negative 3 plus minus and negative 3 square, negative 4 times a is 1 and c is minus 1. So we got 3 square is 9 and this becomes plus 4. So we got 3 plus minus square root of 13. And we can break it down into two solutions, 1 3 minus square root of 13 over 2, and put on the calculator round to 3 decimal places, so you get negative 0.303. And since it's a less than 0, so we ignore it. Probably it's not a solution. You can check it. Now we calculate the other one, 3 plus square root of 13 over 2, and we become 3.303. So the answer is 3.303. Example 16. The number of bacteria in a culture is increasing according to the law of exponential growth. The initial population is 240 bacteria and the population after 10 hours is double the population after 1 hour. How many bacteria will there be after 8 hours? So first we create a formula model so we can answer this last question. So since it's a growth model, so I think growth model, we have a growth model in the book, y equals to a times e to the power kt. So A is here the initial population, which is 240. So we substitute 240 where the A is 240 in this model, and the model becomes this one, y is equal to 240 times e to the kt. Now we still have to find k, so we have this information, k after 10 hours is double the population after 1 hour, which means when t is 10 minus 1 equal to 9 hours, y becomes twice the initial population, which means it becomes 480. So now we rewrite this model here and we substitute t equals to 9 and y equals to 480. So this equation becomes 480 equals 240 times e to the k times 9. Now it's an exponential equation, and we have to isolate this e to the k times 9, so we have to divide 240. So we divide both sides, we get 480 over 240 equals to 240 over 240 times e to the k9. So it's simplified to 2 equals to a to the k times 9. And now we take the natural log, so it becomes the natural log of 2 equals to natural log of e to the k9. Now we apply the inverse property of logs, and since remember natural log has a base of e and this also has a base of e, so they cancel according to this inverse property. So we simply get natural log of 2 equals to k times 9. Now we divide by 9. So we get k is equal to natural log of 2 divided by 2. Now we can use the calculator, and we're going to round to the 4 decimal place. So we get k equals to 0.0770. Now I rewrite the model, growth model, which is y equals to 240 times e to the power k times t. Now we substitute k equal to 0.0770. So we get y equals to 240 times e to the power 0.0770t. Now this is a useful model. If you know the t, we can find the y. Or if you know the y, we can find the t. Let's see. Now the question is, how many bacteria after 8 hours? So it looks like 8 hours means t is 8. So we substitute t is equal to 8 in our useful model. Y equals to 240 e to the power 0.0770t, and this becomes y equals to 240 times e to the 0.0770 times 8. Now put on this calculator and try to get 444.36, round to nearest whole number. So this will be 444 bacteria after 8 hours. So example 17, the population P in thousands of Horrible County, North Carolina from 1960 through 2004 can be modeled by this equation: P equals to 76.6 e to the power 0.0770t. T represents the year, with t equals to 1 corresponds to 1961. So the question is, we're going to complete this table. Okay, what is the population when the year is 1980? When is the population when the year is 1990? What is the population year 2000? We are given the population in 1960 is basically 76.6 thousand. Okay, so now we're going to complete the table. So here's a year: 1980, 1990, 2000. So here we're going to write the model. P is equal to 76.6 e to the 0.0770t. Where did this come from? This was given in the question. So now all you have to do is find the t value. Well, in 1960, t is 0. That's what was in the problem. So we're going to find what is t when the year is 1980. So it looks like from 1960 to 1980, t is 20. So we're going to put 20 here and put on the calculator round to nearest whole number. So we're going to get 357,308. And in 1990, so from 1960 to 1990, the t becomes 30. So we're going to put t 30 here, and we write 76.6 times e to the 0.077 times 30. Put on the calculator round to nearest whole number. We're going to get 7,701. And now year 2000, t becomes 40. So we have now 76.6 e to the 0.077 times 40. Again, put on the calculator, and you should get 1,666,694. So example 17 and part B. Let's say, according to the model, when will the population of county reaches 830,000? So P is equal to now 830,000, but we need to convert into 830,000. So we're going to divide by 1,000. So it becomes 830, and we write the model. P is equal to 76.6 e to the power 0.077t. Now we substitute P equal to 830. This equation becomes 830 equal to 76.6 e to the 0.0770t. Now we divide both sides by 76 by 6. So we have 830 over 76.6, 76.6 e to the 0.0770 over 76.6. They cancel out, and we have 830 over 76.6. So this is equal to e to the 0.0770t. We take the natural log of both sides, become natural log of 830 over 76.6 equal to natural log v to the 0.0770. Now looks like natural log has a base of e and this exponential has a base of e. We can apply this inverse property of log of a to the x, ax base a is x. So this then cancel out, gives you 0.077t. So now we divide by 0.077t. So now we have a natural log of 830 over 76.6 divided by 0.077. We use the calculator and we get 30.9458269. Round to nearest whole number, t is equal to 31 years. Now we're going to write year. Starting year plus t. So we substitute starting year is 1960 and t is 31. So we have 1960 plus 31 is 1991. So in 1991, the population of the county will be 830,000. Part C, do you think the model is valid for long-term prediction? The answer is no. Population increases too rapidly. Valid for years 1960 through 2004.